We're back. So let's talk about biopolymers, the original materials, and always in our minds that these should be future materials too because of easier recyclability. The question is a cost, and personal opinion here, not fact. Might be time to look a little bit at long-term costs and not always at the short-term costs. You are made of biopolymers called proteins. Proteins are made of amide bonds. An amide bond runs from an N to a carbon, carboxy. Okay, so another way to do this thing would be to put an R group there and draw it that way. So usually we're drawn this way though. You have a series of these things. Now, amide bonds are pretty strong, and they tend to lay out kind of in a plane like that, which gives us a certain amount of structure to the polymer chain. In fact, it gives us several kind of characteristic structures. And these R groups, there's some 20 of them, different choices here, and they can be anything. They can be polar, non-polar. They can be acidic, they can be basic. And more importantly than that, in a particular protein, they can be exactly the same in every copy of the protein that a natural living cell makes, and they can be in the same sequence. Okay, so examples of R's would be alanine, glycine, and leucine. I could have alanine, glycine, and leucine in that sequence, okay, in every protein, every time. And I can do that for great long sequences, not just those three. I can have proteins with hundreds of such units or even thousands. And they would all be in a particular sequence doing a particular thing. Okay. But even those molecules, though they're big, have to be assembled. And I think this is the part that everything before is chemistry, kind of. When you get into material science, you have to worry about the assembly of these molecules into other things. And there are various ways to characterize that. Some of these are shown here. Differential scanning calorimetry measures heat, for example. Heat changes can be detected when proteins bind together or change their shape. You can pick that up. Various electron microscopies can be detected. So all these different levels of structure have their own kind of characteristic technique that goes with them. But look what a range of structure. If we went down to the chemistry, it's smaller yet. But I mean, 15 angstroms up to microns, that's an enormous range of structure. Okay, that's really enormous. So anyway, the thing about proteins, they can do almost anything because you have those various amino acids to choose from, and you can put them together any way you want. Okay, any way that evolution has delivered to us. Probably the most stunning example of the functionality of proteins is this business that you're exhibiting right now by burning fuel. Whatever you ate at lunch, the Twinkie or the cookie, is being burned in you. It's being burned just as surely as if you lit it with a match. But you're not going up in flames, and you're mostly a bag of water, and it's still being burned. And this is made possible by the catalytic activity of proteins called enzymes. And just as a reminder, if we have a reaction, I'll just write RxN for reaction, and I have an energy. Most of the things that we want to do to give off energy and drive our muscles and do everything else have a huge energy of activation. And enzymes, because they can have specific structures, can greatly lower that energy of activation. And remember, that difference appears in an exponential term. So it's a huge difference. It's not just the usual. Okay. So enzymes are doing that for you right now, and proteins do a lot of other things. They can do magnificent work in even proofreading nucleic acid sequences. If an error is made in copying a nucleic acids code into a protein, this is basically what goes on, There's proteins that come along and fix that later on. There are proteins that, because of their unique assembly, have high abilities to form strong structures, sometimes in 3D, sometimes in 2 dimensions. It's really quite amazing. So it's so versatile, and yet it all happens in the same factory. Okay, so we have the same problem that nature had the same problem that we have with the polyolefin production and trying to make different copolymers. Our level of sophistication, if you want to call it that, is making a styrene polymer with coisoprene, polystyrene and coisoprene. That's a big deal to us. And we can do that maybe we can do that in the same factory. Woohoo. Okay? Nature uses the same factory, living cells, to make just an enormous variety of things. And it's because there are these amino acids, and there's a good system for encoding which ones to make too. Okay, so we'll talk a little bit about COVID-19. The protein of the year is probably the spike protein. The virus particles do not look like that. They're not necessarily round. They don't have to be. I guess they could be. It wouldn't hurt anything. And they're not all the same size, it turns out. Nature is really good at making macromolecules the same size. It turns out it's no particular advantage to a virus to be all the same size. So they aren't. And on their surface, though, they all have these spike proteins. And it's amazing that we have the structure that you see before you here. It's kind of a complicated looking thing. There's no point diving into it. But I suppose it acts a little bit like the spike proteins on human influenza, which we have studied in our lab a while ago. We were doing that kind of work. And what that one does is it latches onto a cell, and pH-driven processes change the conformation of this protein. It doesn't look like that once it latches on. And so it changes its structure in order to bond. And the COVID-19 protein, the spike protein from COVID-19, which is buried inside this lipid membrane. So the virus is, this giant thing down here. Here's the, it's all underneath that. There's just lots of these on the surface. The COVID-19 protein is designed to hit these ACE receptors. And there are certain receptors on lung cells, and so everybody thought it was going to attack lung cells, which it does. But it seems to be particularly adapted. It's a genetic mutation from somehow. It's particularly adapted to ACE, and ACE is found everywhere in the body, not everywhere, but it's certainly found in blood vessels. So this is a vascular attacking protein too. So that's why so many different parts of the body are getting sick, not just the lungs. Lungs are essential, and once they plug up, we die quick. But this thing can do a lot of damage, even if it leaves your lungs alone. Even if you. So anyway, what's remarkable is that we know the structure, and we know it because of cryotomography. Most proteins are difficult to crystallize. The way that we find out these structures in detail is generally to crystallize something and then hit them with X-rays, which go off and scatter into many points of X-ray scattering that are analyzed with computers. I think almost nobody remembers how to do that manually anymore. And I have that on pretty good authority, that we almost don't know how to do that without our computers now. But in any case, this one isn't even that. A new technique has come along in the last, 15, 20 years, I suppose. Really come on strong lately, called cryotomography. And in this technique, you can do a transmission electron microscopy of this protein oriented in different directions. And then you are able to determine the structure by looking at it in different orientations. You could almost think of it as sort of a shadow graph type of approach, like I get a silhouette from this side, a silhouette from that side, from all possible sides, and I stitch it together. but to do it with 3.5 angstrom resolution is amazing, and to do it in a few months like that is amazing too. In fact, this was done pretty quick. I'm sure they're trying to get a higher resolution structure. 3.5 angstroms is still quite a lot of variation. That means a bond could be here, or it could be 3.5 angstroms away. In the world of molecules, that could be a big difference. So I'm sure there's an effort, maybe even already successful. I do recommend you have a look at this article, and it's a good idea to look at articles even though you are undergraduates. You can read them, just peruse them. You don't have to understand everything. If you start seeing things many times that you don't understand, maybe it's time to look into that a little bit. But I think this one is at least sort of accessible. I mean, it's very pictorial, and you can kind of get an idea what's going on. You don't have to understand. I said peruse, not study, not master. Peruse it like it was your hobby. Okay? So there are 4 levels of structure in proteins: primary, secondary, tertiary, and quaternary. Primary refers to the sequence of amino acids. Suppose I have isovaline, leucine, tryptophan, phenylalanine, and serine. I want them, that's just 5, it could be like 100, but I want those 5 and I want them in the same order every time. That sequence is the primary kind of structure. Secondary is what happens to that sequence pretty much naturally, okay, how it kind of folds up. We'll talk about that. We particularly talk about helical structures and random coil structures are sort of flexible like that, and these kind of crazy things that looks like a corrugated kind of structure, zigzag structure. These often kind of come back and then around, and pretty soon it looks like you have a piece of galvanized roofing up there or something like that, you know, corrugated sheet. Tertiary is how the whole unit gets folded back and maybe comes back and makes crosslinks, internal, intramolecular bridges. Quaternary is how the blobs result from tertiary and all the previous ones, how they may assemble. This slide may help a little bit. Here I've drawn sort of randomly a protein. Here's a secondary structure is helix. I'll use 2 dot for secondary. Okay. Here's the little zone, not very extensive but small. Sheet. Okay. And here's this zone here is the secondary structure. This is called coil, which makes absolutely no sense. The coil should be the helix, right? But it's a random coil. They borrowed this notation from polymer scientists, and I don't know. We said that the chains kind of coil up. I mean, as opposed to being that, I guess you could say that's coiled up. But helix is the one that looks most like a coil to me. But anyway, what can I say? So it's the notation we deal with. There's a little better structure of the beta sheet, you know, showing that corrugated roofing effect that I was saying on the previous slide. Alpha helix is kind of this kind of a screw. They tend to go one way, helical. There are other helixes. This is the most common one. Alpha helix is the most common one. Okay, so here is a tertiary structure for a disulfide link between 2 cysteines, perhaps, and that takes this whole side of the chain and that whole side of the chain and holds that loop together. So that's tertiary structure. And then I think when I designed this in PowerPoint, I drew this out kind of badly, and I cut and pasted another one and rotated it. So anyway, I have a blob here and another blob here. The assembly of these blobs can be kind of particular too, because they have certain shapes. Just think about building blocks. You can like put them together in certain shapes. So that's the quaternary structure. If I'm interested in how that goes, that's the quaternary structure. Here's a list of some of our amino acids. Some are aliphatic, really oily. You know, these are really oily, which, you know, means kind of nonpolar. These ones are just called nonpolar, which means that they're, I guess, they're more polar than aliphatic. This is an increasing polarity this way. Okay, until we get to charged units, which are really so polarized that an electron has been lost somewhere or gained. Okay, so I guess we could count how many there are in this list: 4, 8, 12, 16. It looks like 20 amino acids. I think there's some unusual amino acids, and people are forever making new ones, by the way. Anyway, in addition to the proteins are the nucleic acids. And there are RNA type and DNA type. The DNAs here are actually shown as double-stranded, so they're actually in a helical form. And it's kind of, geez, there it goes. Get a different color pencil here so I can write on the wheel. What's that about? Here we go. Let's see. Notice that this is the backbone is the same. Okay, it's always drawn like that. It's drawn on the outside, which is a point of historical interest, by the way. And the bases are shown on the inside. So I'm circling the bases. These are called bases because they have aminos on them, and aminos are bases. Okay, and it's always ATGC, ATGC. Okay, that's the code. A and T always react together to make the chains that way. RNAs have similar situations. Here is a base, a uracil base on this one. And is shown as a single-stranded helix. Okay. And the beauty of these systems is the incredible interlocking capabilities of these base pairs. Okay. A and T always go together. G and C always go together, right? And it turns out that you can define which sequence of amino acids you're going to get by codons made of 3 of these in a row. The 3 of these in a row in a particular sequence of bases specifies for certain primary code, for certain primary sequence of the amino acids. Because that's all very interesting, and it's actually got important material science uses. One of which is demonstrated by this slide out of the Hannati-Sleeman lab up at McGill. This kind of work, I think, was launched maybe 25, 30 years ago at NYU in Ned Seaman's lab. And Hannati-Sleeman is a kind of a student of Ned, I think, and much more modern, and they're both doing amazing stuff still. And his one comes out of Hannati's lab. And you see she's made this DNA cube. She has figured out how to make the DNA molecules into this sort of cubical shape. And she gets them just the right size because there's a very precisely defined size for these base pairs. How thick it is from one base pair to the next, and that size is 3.4 angstroms. Okay? And so you have a certain number of them, you'll have 3.4 angstroms. And she takes an appropriate sized gold particle and figures out how to latch that onto that gold particle. And then she can cut that loose, I guess, and make this sort of lunar roving type machine. You can have a lunar lander type thing. And these sequences can be designed to recognize other things in nature or other things in a bio production, biomaterials, materials biomimetic lab. And also, it's quite important that these structures are held together precisely but reversibly. If you heat them up, they fall apart before the whole chain falls apart. So you can heat them up. Anyway, so she has this thing here, and it can go off circuit. If these have different DNA sequences down here, I guess I could go back now to a pointer. If these DNA sequences here are designed right, it can go looking for certain DNA sequences like the ones that are made by COVID, okay, or any other infecting agent. And so it can find those things. And you can find them because they're going to be attached to this gold, and the gold has spectral properties that we can see in a spectrometer. So that's just one application. It's also important that these things are reversible because this is how important in the PCR process, the polymerase chain reaction process. Now, if I can have it, I'll have a pen back again. Come on, pen, really? Okay. Chain reactions, that's what you usually think about that as something that's going to blow up on you. Okay? So you have something that reacts, and those reactants react, and those reactants react, and pretty soon you have an explosion like a nuclear weapon. PCR is like that in the sense it's not going to explode on you, but you're going to take one strand of nucleic acid and divide it into two. And you're going to make copies of that. And you're going to go 2, 4, 8, 16, 32, 64, 128. And pretty soon you're at a large enough number that we can detect them. Okay, so that's how we can detect incredibly small amounts of some nucleic acid that's indicating a disease or indicating that you were the person who pulled the trigger on that pistol. Criminology labs are using this as well. It may be of some interest for you to know that this method was invented by a guy named Kerry Mullis, who is a GT BS chemist, alumnus. He did that work, and he just had an inspiration on the way home, driving in his car, a Honda Civic. He was working for a company by then. He'd gotten out, and he had this idea, I can make these multiply. And very soon, that technology was put to practical use and patented. And he got a Nobel Prize out of this, so he is a Nobel Prize winner. So it's quite an achievement for Georgia Tech. He's quite a controversial character. I highly recommend you look up his Wikipedia page. He is not exactly politically correct, which seems to run in the family of DNA type people. I don't know what the deal is with that. But anyway, he is not politically correct. He's quite interesting. But we owe him a lot for this reaction. He's going to save a lot of lives, and he's going to put a lot of criminals in jail. And he's going to get a lot of people who were wrongly convicted of crimes out of jail. Okay. So one way to look at these nucleic acids is a build sheet. Okay. So here's a build sheet for a beautiful 1965 Plymouth Barracuda. And that one is specifying power steering that I just circled, and some of these others are specifying other things. It's really a great thing if your car has the build sheet. It increases the value of the car. Well, we have this DNA complement in our cells is large by the number of repeat units, but it's actually very tightly bound together. And I just got done telling you a little while ago about polyelectrolytes and that ions could come in and kind of mitigate those charges. Well, DNAs and RNAs are negatively charged, and so your cell complement includes molecules that have like +2 charges in them and even higher charges, +4. Okay, and they help the DNA to really tightly coil. So here's a DNA, and you get these molecules that really tightly make this thing. So every living cell in your body has about 1 meter, maybe 1.5 meters of DNA in it. It's just incredibly compacted so that it's in the middle. It's not even occupying the whole cell. It actually occupies a pretty small part, usually in the nucleus of the cell for eukaryotes. So anyway, amazing stuff, huge molecules, functional on all levels, information for DNA, structure, even for DNA now. Okay, nature didn't do that. Nature didn't see that opportunity as far as I know. Ned Seaman and Hanadi Sleeman saw that opportunity, and others have now too, of course. Structural for the proteins, of course. Enzymatic function. There are other functions like structures, enzymes, proofreading, as I talked about. Okay, so because it's Georgia Tech and we have this enormous effort in cellulose nanocrystals, I will just mention another kind of biopolymer, or maybe it's a bioparticle. I tried to convince a funding agency once that it was a bioparticle, but they said, no, it's a biopolymers and we don't do biopolymers, so I didn't get that money. Too bad. I'm going to blow this up. I think it's a little hard to see the possibilities here, unless I do. Let's see. Look at these things. You can see down there the scale bar. I'm trying to draw a scale bar. It said 200 nanometers. I don't know if I can get rid of it now that I got it. 200 nanometers, that's 0.2 microns, 2,000 angstroms. Well, that's a big, heavy structure as things go. It's bigger than most molecules. Some macromolecules, I said, look how straight it is. Well, when a polymer scientist sees something that straight, they think, oh, that should be a great fiber. I should align those. Or maybe I can turn that into a liquid crystal. So any material scientist is going to see that opportunity. So these things can be made into liquid crystals and ultralight, ultra-strong materials, stronger on a mass basis than steel. So there's a big effort on that here at Georgia Tech. You can get involved in those things. See me about that or see some other people. There's maybe 30 people working on those here. It's amazing. Gels. All right, we're going to blast into gels. Gels is so cool. I want you to do a thought experiment here. Let's see what I got here. If I get a, what color pen do I have? Let's go with blue pen. This is going to be a beaker. Okay, so there's a beaker. It's full of water. And inside over here is a polymer. It's hugely magnified. Of course, I can't show you a single polymer on the scale of this. Okay, but it's growing. And let's say that it branches. Oh yeah? Really? Let's let it branch. And keep branching. Even the branches branch. Many times. If I can branch enormously like this, put some up here towards the other side, toward the back of the beaker, towards the front. Branch, branch, branch. Remember we started around here. Okay? That means I can get on, if I could walk this polymer. Imagine I could walk this polymer. I'm going to walk it. I'm going to walk it with ready, leave little breadcrumbs and walk along this polymer. I'm going to go everywhere on this polymer. And I want to get up to the upper right corner. I can do that. And from the upper right corner, I could backtrack. I have to work my way back so far. I can backtrack all the way and I go to the upper left corner. Now, if I also form cross-links, so far I just branched it, just branched the snot out of it. But I could make shortcuts, right? I could make cross-link shortcuts. And there are chemistries that do this, and it's been studied a lot. And there are natural things that do this. So now I can really get from any car, I can get on wherever I want and go wherever I want, right? I don't have to always go back to the starting point. Like, I don't have to walk backwards. I can start at this side, come up, and go all the way over to here, and then I can just kind of zigzag my way following the trail, and I can wind up over there. It's one giant molecule. That's the point. At this point, I've made one giant molecule. Let's suppose I did that with 1 gram of polymer. And I did that in 99 grams of water. Okay? But it's 1 gram of polymer, and it's one molecule. So that means its molecular weight is 6.02 times 10 to the 23 grams per mole. Effectively infinite, right? If I had a bigger container, this thing would have a molecular weight bigger than the mass of the solar system. Okay? Or at least the Earth. So that's kind of amazing. One giant molecule, especially with the crosslinks, shortcuts built in, could be this huge molecule. That's a network, and that's how you get gels. And, what should we say about gelatin? Let me ask you a question. Is it a solid or a liquid? And that very question was asked to me on my PhD candidacy exam, which was an important place to, would have been nice to have a good answer to that, and I really didn't. So I did some of my work in gels and for my degree, and well, I have a better answer now. It's kind of both. So if the question is, one more song, I guess. Talk about how it works. How do we get that to happen? And then we'll talk about solid or liquid. Okay, how do we describe this thing? Okay, now we're going to have my pens working for this, and hopefully it works. Gelatin is collagen. Collagen is piglets, horses, cow ears, and it's a stable triple helix. And the easiest way to draw triple helix is just to draw zigzags that intertwine like this. I'm doing the best I can. So this is a collagen from the name, Kala is going to be something like sticky, and gen, generating stickiness. So glue generating thing, colloids. Same root word, I believe. So that's a collagen triple helix. Now, it suits my purpose to draw these in different colors. So I'm going to draw another one. That first one I'll continue to draw blue. I'm going to draw it a little bigger. The next one I'll draw red. There I sing. It just helps us understand what's going on to make them, I guess, a little dark green here. Okay, so it's the same as the all blue one, it's just that it's going to fly apart in a minute. We can track what happens next, okay? So let's go and choose a red palette. Let's heat this up. Red. Why red? Red is hot, that's why. Okay. Now, I should have put in water everywhere. But not a drop to drink, because it kind of, at the scale of your mouth, it's a solid, right? At that scale, it's a solid until you chew it or melt it. It has a lot of water in it for a solid, but it is solid on that scale. Kind of hinting. And all these dots, remember, are chevrons. Water is a chevron molecule, right? H. So, just too many to draw. So, we heat that up, and here's what happens. The protein adopts random coil conformation. Switches. Random conformation. And remember what I said. This is only compared to being laid out straight or something stupid like that. Okay, I guess it would probably be better to turn the camera on so I can... Come on. Really? There we are. Now I can wave my hands and stuff again. Okay, so how gelatin works. Well, the next thing you do is cool it down. What color should be cool? I don't know. Okay, so we're going to see over and over in this course that when you cool something, if you cool it quickly, it will not have time to get all the way back to equilibrium. The triple helix structure that we have here, this triple helix, stable triple helical structure, is made inside nature's system, nature's factory. Okay, but we're going to cool it quickly, and we're not going to give it time to achieve that level of perfection. And still, it's going to want to coil up, though. I mean, go from random coil to helix. It's going to want to helix up. So what's going to happen is that regions from one chain are going to come to another. And then I remember I have lots of these. Okay? So I have a lot more than the three I showed. And I can have a blue one interact with another blue one from some other collagen triple helix that I destroyed. Okay? Or I can have it, because blue is the same as red and green, I can have it link up with red or green. So it doesn't matter whether it's red, blue, green, and it doesn't matter whether it came from the same, whether it comes from the same original triple helix. None of it matters. It just doesn't matter. But what happens is this sort of thing. Because you don't give it enough time, it only can make these helical regions in a small zone. Okay, small zones, multiple zones. Okay, so here's a red one. It's off. Okay. Here's a green one. Have a green one come in somewhere here. Okay, it comes in here. And it maybe interacts with this blue one over here. Okay. And remember, like I said, I have lots of these from different chains. I can have one come in here. Let's say I need a red for that one. Have another red from some other triple helix come in through here. And it can go join a triple helix there with this one. I'm going to have red and red. Because they're different chains now, it doesn't matter. But they're going to be triple, so I can have, you know, two reds and a green here. These are just crossing sometimes. Maybe they want to, I should put it, make it go below. Every now and then I'll make one go below, huh? Okay. This one goes over the top. That one goes below, comes down here. Squiggles. You know, it doesn't matter how you draw this. I hope you're not trying. I hope you're drawing it. I'll help you remember what's going on. But you don't have to get it the way I do. That doesn't matter. And so that's what gives our gel structure. Now all those little water chevrons are still there. They're still there. And the rest I'm just going to draw by little dots, lots of dots. So the guy on my PhD defense who died a few years ago, he was a really great guy. Nice man. Theorist, polymer theorist. He asked me because he was German. He says, well, is the gel a liquid or a solid? And I sat there like a dummy. The right answer would have been to be like a politician and prevaricate and say, depends. In this case, that really is the right answer. And then they would say, well, what does it depend on? Okay, so what it depends on is scale and time. Okay? These are supposed to be asterisks. Depends on scale and time. If you ask me how fast the water molecules are going, let's say we did this at, like I said, 4% and 96% water. Okay? Suppose we did it just like that. The water molecules are going almost as fast as they did before the gelatin was there, almost as fast as pure water. To the water molecules, it looks like a liquid. Okay? How do we even gauge that? How do we even gauge that? All right, so let me answer that a little bit, and let's see if I can put that on the same slide. If I'm lucky, I might be able to do that. Is it a liquid or solid? Okay, so the water molecules, they're still moving, okay? So let's look at the water molecules. And there's, you know, multiple kinds of motion. There's stretching of the bonds, there's various kinds of rotation, there's various kinds of motion. But let's just talk about in general some sort of, garden variety rotation. So this thing could be rotating. Okay, and it turns out that this is probably 10 to the 12th. This is all approximate. Rotations per second. Okay, why don't I say radians per second? Okay, you could say turns per second, it hardly matters. This is going to be approximately tuned to your microwave that you heat food in, by the way. Okay, it's operating at about that frequency. Okay, so it's giving off microwave radiation at about that frequency. The other thing that's more of interest to us really is translation. So this thing moving to the right. Okay. As often as one moves to the right, one will move to the left. Because there is no net motion of the beaker. Okay, so the water in the beaker, some is going right, some is going left, some is going up, some is going down, some is going in, some is going out. Okay, so there's no net displacement of water molecules. If I was to look at all of them, there would be no net displacement. I am equally entitled to look at just one of them for a long period of time, and I would see sometimes it goes left, sometimes it goes right, sometimes it goes up, sometimes it goes down, sometimes it goes in, sometimes it goes out. But overall, it goes nowhere. The average displacement, this is a bracket here, the average delta X. This is a bracket, not a water chevron. This is a many particle bracket. Or it can be one particle okay? And those are the same for most samples, okay? Whether I calculate the average displacement, I could do delta Y. I could do average displacement of delta Z. I could do all of them, okay? They would all be zero. Whether I calculate by looking many particles at an instant in time, or one particle over a long period of time. Okay? Those are usually going to be the same, and that is known as the ergodic hypothesis. Let's not call it a hypothesis. Let's just say that for most systems it's true. Okay. For many systems it's true. So that's an ergodic system, right? But in any case, there is no net motion. And yet, I tell you, these molecules are moving. They're moving. And in fact, they're moving almost as well as they did if the network was not present. So the way that we keep track of that is by not monitoring delta X, but by monitoring delta X squared. Let's draw a better bracket here. Right? That's finite. That takes out the sign. Because the reason that these were zero is that sometimes they move left and sometimes they move right, and it cancels out if you look at delta X. But if you look at delta X squared, it's always something there. So some of you have had circuits analysis, and you've seen this kind of thing before. You've seen this kind of thing before, believe it or not. Okay, wow. I did not mean to magnify. Okay, if I look at the line voltage in an AC circuit, it does this. Okay, or if I look at the current. Okay. So there is no net voltage, there is no net current. And that's true to a point. Okay. The electrons that were in your wire that your lamp is plugged into are the same electrons that were in there when they made the wire. They just sit there going back and forth. And yet there is power, right, coming out of your wire. So the way you do this is you look at V squared. Pick a different color. I'm just trying to convince you that this is not such a foreign concept here. Okay, so V squared looks like this. Right? So there's always something there, even though on average there's nothing there. Crazy. All right, so, and that's the beginning of a rectifying circuit when you have an amp. The first thing you have in an amplifier or many devices, LED lamps, is to rectify that circuit, turn it all into positives, and then make it into a DC current, which we're not going to talk about the rest of that, but anyway. All right, so this delta X thing, that is finite, and it turns out that there's a thing, if I divide that by time, then I can actually calculate something like, really want this over here, a diffusion coefficient. And this is actually going to be a self-diffusion coefficient. We'll talk about other kinds of diffusion coefficients eventually. But this is just the water molecules moving around and not really changing the overall concentration of water. It's water everywhere, but not a drop to drink because it's basically a solid on the scale of your mouth. All right? So we usually write this with a 2 here, and then we take that out, but it doesn't worry. Just leave the proportionality constant there. And the units of this is going to be centimeters squared per second. So this is our first self-diffusion coefficient. This is our first diffusion coefficient. Self-diffusion coefficient. And the water value is about 10 to the minus fifth square centimeters. Goodness, I need that to be an M. Square centimeters per second. And that's probably the fastest diffusion coefficient you're going to see in this whole course. Okay? We will talk about diffusion in metals, and it's going to be massively slower than that when they're in solid form. Okay? So that is a fast as heck diffusion coefficient. The diffusion coefficient of the polymer chain is 0, basically, almost 0. Approximately 0 in the gel state. Okay, so is it a liquid or a solid? Well, to the water, it looks like it's liquid. The water can hardly tell anything has happened. The gelatin did have a diffusion coefficient in this state. Before it was, when it was in this melted state up here, it had a diffusion coefficient of maybe 10 to the minus 8th square centimeters per second. And it goes almost to 0 once the gel happens, once the gel forms. At least most of it does. There are, by the way, little bits of gelatin that hang around and don't ever join in. So those ones are still moving. Nevertheless, the structure of this is so fine, think of it like a sponge, but a very fine sponge with enormous surface area, and it kind of holds the water in place so that when you drop those gel cubes onto the surface, they just sort of bounce around like they were solid. The water doesn't go spilling out. It doesn't happen on that scale. Okay, so on the scale of the gelatin cube, it's kind of like a solid, but a very softish solid. On the scale of the water molecules themselves, it's like a liquid. What are we to make of this? Okay. So let's talk about that. What's the difference between a solid and a liquid? And that's explained with this diagram here. Okay, let's begin with the solid, which is on the left. And this is liquid. Okay? And what we're doing to this poor solid or poor liquid is sort of applying a force that's a shear force, like this. That's called shearing. So if I was to take this bit of this electrical tape that I have sitting here, I'm sort of rolling it, aren't I? Okay, if I'm taking this little clock and shear it, what if I put in Jergens lotion? Let's do that this way so I have softer hands, right? That's a shearing motion. Let's talk about the forces that are required to do that. Let's suppose we do that with a solid like an eraser. I think I actually have one, believe it or not. I do have an eraser. My goodness. It's kind of fortunate. This is not planned. Ooh, this way. Okay. If I shear it like that, it actually bends in this sort of shape, right? You sort of see that. But it's this one's kind of old and hard, but it's still a little springy. It'll spring back. It'll spring back if I do that. The gelatin sprung back. Okay? So what we do is we're applying a force, okay, F here, in that direction. And then this surface that we apply it to has area A. Okay? Right? And we define tau to be F over A to be the shear stress. There are far too many S's in this development, and there's nothing I can do about it. Okay, the other S that exists here is strain, shear strain. This is gamma. This is dy by dx. You can say, okay, we moved it, we displaced it a distance dy, and the thickness, the original thickness of the thing was dx. So this shear strain is unitless. It's See how many S's there are? Shear strain, unit less solid. Geez, what a mess. So many different S's. It's all about S's. Okay. It turns out that tau is proportional to gamma. Shear stress is proportional to strain. You have seen this before, and it was called Hooke's law. Only it wasn't for shear. Okay? Hooke's law was done this way. You did this. In basic physics, somewhere you've done this. We have an object. Here is the object. Let's just pull it straight. So instead of a shear deformation, we'll have we'll just have a stretch of this spring. And we pull on it, and the spring gets longer. I should have made the spring, it's a crappy spring for this purpose. The spring should have the same number of turns. That's going to be conserved, I think. So we'll make that's better. So we displaced it by delta x. Okay, and we said F is K delta x. And we said this was Hooke's law. And if we release that force, it'll snap back, because that's what elastic springs do. If we release the shear force on this sort of originally cubical object, it will snap back, because that's what elastic solids do. Instead of Hooke's constant K, we have shear modulus. Okay, G. That's the shear modulus. And I can't write that close to the bottom. Shear modulus. All that energy that we put in by stretching the spring is stored, right? The energy of doing this is K delta x squared over 2, right? We integrate f dx, and that's what we get. So there's a storage energy there. So this shear modulus is actually called sometimes the shear, it should be called the shear storage modulus. I don't think I have. I'll try to write that. Shear storage modulus. I'll just write shear storage. That's enough. Now we have to compare what happens with the liquid. Same basic geometry. But if you think about it, if you put the Jergens between your hands, it's easier this way. Put the Jergens between my hands, I actually have to push it apart. But as soon as I stop, it's not like it slaps back. What if it's shampoo or soap or anything? I push it there, anything liquid, and I actually have to push it to spread. I do have to push it a little bit to spread it. But when I let go, nothing happens. It doesn't snap back. So in this case, the force, again normalized by area, tau, still force divided by area. In the case of the liquid, it's not proportional to the strain, it's proportional to the rate of strain. It's proportional to that pushing of the liquid, displacing it, okay, per unit time. To push it further, you have to use more force. I mean, to push it faster, you have to push more force. I said it wrong. To push it faster, you have to push with more force. Okay? So instead of tau being proportional to gamma, is proportional to d gamma dt. Okay, and the constant of proportionality, instead of being called shear modulus, is called viscosity. That's what viscosity is. It's tau per gamma. Okay? It has totally different units than the shear modulus. And the name that goes with this is Newton. When eta is tau over gamma dot, that is a Newtonian fluid. Polymer fluids are not always Newtonian, but they're close enough for our purposes. We're not going to get into that just now. Okay, it's actually very important that they're not Newtonian. All right, so what is any actual material? We saw the solid gel cubes. Once they were falling through air, they looked like solids, and when they came down and hit the table or whatever they were bouncing off of, they distorted a lot, but they bounced back. But they would not have bounced back and forth like this. They would not have bounced back. Some of that energy is delivered back, so it can bounce a couple times maybe, but then it's going to pretty much stop, right? So this is not elastic. The opposite of elastic is viscous. The opposite of storage is loss. Okay? So there's actually a thing called the loss modulus that goes with the viscosity. Okay? It's not the viscosity, but it goes with the viscosity. So you have storage of energy, you have loss of energy. In any substance you care to name is a little bit of both. Everything is viscoelastic. Everything is viscoelastic. So what I should have answered on my PhD examination is, well, it's a viscoelastic solid. Or an elastoviscous liquid. You tell me. Okay. That particular professor would have loved it if I'd have given some sort of off-the-shoulder snotty remark like that, and I should have done it. Okay, because they want you to be thinking on your feet. They want you to be sharp. I guess I was sharp enough on other parts of the exam. Anyway, so viscoelastic solids. Nowhere is the visco part of viscoelastic more obvious and more important than in polymer science, I think. Okay? If you're looking at pure fluids, you know, gases running through a jet engine, gasoline running through a carburetor, whatever you have, those are viscous fluids, yada, yada, yada. People understand that. If you're looking at bending of hardened springs, in a camshaft or a suspension or something, that's elastic. People understand that. Viscoelastic just sort of happens in polymers a lot. It's our milieu. It's where we live in polymers. Okay. So we'll talk about this some more later, and we'll see that this happens. But anything is viscous, anything is elastic. It just sort of imagined, depends on how fast you're going. So let me, and the size. Okay, it matters on this. It matters what size, what scale you're looking at, and it matters over what time frame you're looking at. Think of a glacier. A glacier is a flowing river of ice. Does that make sense? Ice is a solid, but this thing flows on some time scale. Okay, if you don't like glaciers, and if you don't think, if you don't understand this business about the time, the dynamics of the situation, you can look at a swimming pool. If you dare go near one in this COVID age, you can go near a swimming pool, go to the diving board. I would recommend a fairly low one, and do your best dive and belly flop. And you're going to hit that flat surface of water fast enough that it's going to seem awfully much like a solid. And in fact, if you do that from too high, you'll kill yourself, right? This is not a good thing. You might as well just dive onto concrete if you go fast enough. So it's always about the scale of the object. It's always about the speed of the deformation, whether it's viscous or elastic. Okay? Okay. One other thing I want to show you about this is buried in a Excel. And I think I can get that to work here. I embedded it into the PowerPoint, so I shouldn't have to go hunting for it next time. I'll open that up and see what it does. I don't think I need all that just now. Let's see if I can get rid of some of this. So it opens as a nice Excel window. And what we're looking at is stress. The total stress, that's tau in our units. By the way, other disciplines call this something else, and you just have to deal with that. And that is the total is the sum, so that's the yellow line. And it's actually the sum of a sine term and a cosine term. And so what we're imagining that we're doing here is that we're running an object like this in a sinusoidal motion, right? Right, so we have a sinusoidal stress, we have a sinusoidal strain, right? We also have a varying shear rate. Now, when I get to the left edge, the system stops. That's my maximum stress due to the elastic term, okay? But in a viscous sense, I'm no longer pushing on anything. There is no viscous force at that point. That happens in the middle somewhere. Okay? So the elastic term and the viscous term are 90 degrees out of phase. And when you take things that are out of phase and add them, the sum is also out of phase. Okay? It's some phase. It acquires a phase sort of in between. So I think if I am smart enough, I may be able to shrink this down to where we can have some fun and change some numbers around. That was 40% elastic, 40% storage, and 60% loss. So I'm only going to change the elastic component, which is 0.4. I'm going to change that to, let's change it to 0.85, just for the sake of argument. So that means there'll be 85% elastic and 15% lossy viscous motion. Okay? So now we see that the sum in yellow is tracking more closely to the sinusoidal in-phase term, which is the elastic thing, which let's say that's the sine term. If the gamma strain is a sine, then d gamma dt, or gamma dot, is a cosine, right? D gamma. D sine of something, d something is cosine or something. So it's 90 degrees out of phase, but it only contributes weakly because it's only 15%. So you can kind of gauge the amount of loss that you have with these two numbers, 85% and 15%. But they're really tied together, right? 85% and is, 1 minus 15%, or vice versa. What's actually done in practice is to calculate tangent of delta. Okay, so let delta be the phase angle difference between them. In this case, it looks like 10 degrees. Okay? And tangent is delta. And we look at this tan delta number, and let's run it up to see how that behaves. We'll make it be 0.995. So that's 99.5% elastic. Tan delta is 0. There's no phase lag. It's in phase. The response, the force is in phase with the displacement. Okay? Let's run it the other way. We'll make it 0.001% storage. Now it's going to be almost a real liquid. Now the delta is 90 degrees. Okay? Delta is 90 degrees. Tan delta is some large number. Okay? Higher tan delta, the larger the loss. This is called the loss modulus. And this is used to characterize actual fluids, including polymer melts. For all I know, it could be used to look at molten melts of steel. I think it'd be a lot less interesting. But it could happen. But I'll tell you where it's definitely used. It's used in capacitors. Sitting on my shelf behind me, on the shelf over there, because I'm in my shop here, is a bunch of capacitors. And you go to the Newark catalog, or Parts Express, or any of them, or Amazon, and you order some capacitors, and they'll say, what tan delta value do you want? How good a capacitor do you want that to be? Do you want it to store all the electrical energy? If you do, you might expect to pay something for that. Or do you want a cheaper capacitor, save some money, and good enough? Okay? So this basic idea of storage and loss applies in rheology, it applies in electronics. And there's a lot of things like that. There's only one physics. That's why these guys think they're the kings of everything, because they actually understand that there's only one physics. Okay, so, all right, let's see about that. Let's go back to this and see where we are. This is the same kind of thing, it's just a different set of sort of different way of looking at it, sort of a two-dimensional cross-sectional view. I will point out, I'll take the opportunity to point out some things here that are kind of important. There is a flow profile in here. We introduced gamma dot as d gamma dt, where gamma was delta y over delta x. Okay, fine, same thing is holding here. But you could also look at it as a velocity profile. And for many fluids, the velocity, this upper plate has a velocity v. The little molecules that are near the top there are moving at velocity v. And that's actually called a stick boundary condition. The molecule velocity is the same, okay, as the plate velocity. Okay, so here u would be 0. V is 0. Here, this is the stationary plate. It's important to know that in certain systems, that doesn't happen. There are called slip conditions. I guess that could be good or bad. It means things slips along. You don't have to worry about spending the energy to accelerate those molecules. They're just going to slip. All right, that's enough about viscosity for this class. But we do want to say a little word about an important quantity in polymer science called intrinsic viscosity. You may see it, and it's important to know that it is not the viscosity. It doesn't even have the same units of viscosity. That's probably the main thing to know about it. It's historically important, and it tells us the following. One of the most tangible features one of the best features of polymers, and one of their most inherent features, okay? One of the best features and most characteristic features of polymers is the ability to add viscosity to a liquid. You want your motor oil to work right? This is what you do. And historically, this was very important in determining that polymers even existed, so you'll hear it all the time. From a physical point of view, what this intrinsic viscosity is, it's sort of like the hydrodynamic radius of hydrodynamic control. Okay, so it's what volume of liquid is controlled by the polymer per unit mass. Okay? And it's enormous for polymers. It's just enormous. It's unlike it's not like anything else you can think of. And the analogy that I like to try out on people is to go back to the idea of throwing a cat through a tree. You can't do it. You can't even throw a baseball through a tree. Try it. It's not easy. Okay? And if you ask what happens if you try to get wind through a tree, you can. Air molecules go through a tree. It depends on the rate. The slipstreams are remarkably around the tree, though. You mechanical engineers are definitely going to understand this better than I ever could. Okay? If you don't believe that, I recommend this experiment. Remember, we're trying to find the joy. And one way to do that would be to go up here and sit in a tree and do it with a nice book. Draw a book in there. And don't go too high in the tree because you'll hurt yourself if you fall out. Okay, maybe just go up a little bit. Get yourself a ladder if you need to. And go up and do this. I walked out of my office in Georgia Tech one day, 2 in the morning. And there were 2 girls up in a tree at 2 in the morning just chatting and having a great time. And that was 2 in the morning, and I don't know what they were talking about, but they were having a great time. And it was not a windy day, but if it had been, I don't want you to do this in a hurricane. I want you to do it in a light breeze. It's not silent. There's a breeze comes into the tree, but it's not a lot. It's pretty quiet in there. Polymers hydrodynamically own a lot of fluid. And this is what it takes to contribute to viscosity. So polymers have enormously high intrinsic viscosity. It's the inverse of density. That's what this is, isn't it? It's radius over mass. Radius cubed is a volume, so it's volume over mass. That's like an inverse density. So you can think of this intrinsic viscosity as a inverse hydrodynamic density. And it's important to know that polymers have that in spades. That's what they do. It's why we add polymers to food. If we want food to not just gush out of the bottle, we want to pour out, and we say, oh, it's thick, it's rich, it's best. No. It's just that we added some xanthan in there and made it that way. Shampoo, same thing. Okay. I'm going to stop at this point and post these, and we'll pick up here in the future. Thank you so much